It's really not. We probably gonna.
Partial fractions. Interesting. Right, yeah.
Yeah. Actually, yeah. It's like I didn't have a very good song.
Chapter 8. 3D stuff, vectors, that kind of jazz. Let's go ahead and talk about. We'll talk about a little bit of 3D graphing just because there's kind of like a tiny bit of that, and then we'll move on to vectors pretty quickly. So let's talk a little bit about graphing in 3 dimensions. Let's plot some points. Let's say we want to plot the point. What's that? 7.3. So, which is what, Euler's method?
Yeah.
Did you guys cover Euler's method? Oh, I didn't seem to that at all. Okay. Sure, let's back it up. Sorry about that. We'll come back to graphing in 3D a little bit later. Yeah. Okay, let's see if I can find my notes here. I think I left them in my office, unfortunately. That is unfortunate. Euler's method. Let's see. Let me look real quick for 1 minute. Well, okay. So the idea with Euler's method is you're trying to estimate the value of a function based on the differential equation that we're not going to typically solve. So let's give ourselves a somewhat easy example. So let's say we have the following. Given that the differential equation is say dy dx is equal to x plus y, and you typically need an initial condition as well. Let's say we're given that y of 0 is equal to 2. 2, sure, fine, we'll live with that. We want to estimate y of 2 using steps with size, and we usually call this h for whatever reason. H equal to, let's use the typical choice of 0.5. So that's usually kind of the setup. So what are we actually doing here? Regardless of like how you actually accomplish it, the idea is that we're going to do the following. We're going to start at our initial value. Let's go, we'll mark this off in sure. So let's go smaller than that. Let's say that's 1, that's 2. So there's our initial value, where y of 0 is equal to 2. And the process is going to be the following. At that point, I'm not going to draw the direction field because drawing the direction field is terrible. But the idea is at that point, we're going to find the slope of the direction field. And then we're going to go in that direction over our step size of 0.5 and up whatever we need to accomplish that slope. So let's actually do it. So at 0, 2, what's the slope? Well, the slope is going to be the derivative. It's going to be dy dx evaluated at x equal to 0 and y equal to 2, which in this case is just going to be 0 plus 2. Now, am I doing this the longest way possible? Yes. We're going to streamline this a bit, but for now, we're just going to kind of understand what we're doing. So our slope's 2, so we're going to go step size of 0.5. We're going to go over and up a slope of 2. So if our slope is 2, that means our rise over our run is equal to 2, but our rise is what we're trying to figure out, and our run is our step size, which is 0.5. So it looks like we're going to increase our y by 2 times 0.5, which is just 1. So we're going to go over 0.5 and up 1. Now we're at the point 0.5 comma 3. And then the idea is we kind of just repeat this process every time. Now we're at a new point. At that new point, we find the slope there, and then we figure out whatever our rise is going to be based on whatever the slope is. So now we'll do it one more time, kind of this long way. So now at the point 0.5 comma 3, we have that our slope dy dx is going to equal 0.5 plus 3 based on our differential equation equal to x plus y. That's going to be 3.5. Our rise, I always think of it as the rise, right? It's how much y is increasing by. Our rise is just going to be our slope times our run, which is our h. Our slope is 3.5. Our run or our h is 0.5 every time in this example. H never changes in each example. That's going to be half of 3.5, which is 1.75. So now our new y value is our old y value of 3 plus however much y is increasing by 1.75. So we're going to go over a half and up 1.75. So now we're at the point 1 comma 3 plus 1.75 is 4.75. That's the idea that we're doing here. And then we just keep doing this until you get to the right y value. Now, the way I'm doing it here is kind of messy. Let's make it a little bit more tabular. So I would usually make this into a table. So here's kind of the more general way we process this. We're going to think of dy dx equal to x plus y as our f of x comma y. This is what the notation they typically use in the textbook. And then we're going to say that each subsequent y value, so the new y value, our y sub n plus 1, is equal to the previous y value plus the rise. The rise again is your run, your h value, your change in x, multiplied by your slope at the previous point. The slope being f of x sub n comma y sub n. When I first saw this formula, it's kind of like that. I don't really understand what's going on there. But now that I've thought about it, I'm like, oh yeah, you're just taking your old y value, adding on however much you're increasing the y part by, which is just your slope multiplied by your run, right? Here's our run, here's our rise. So let's make a table and kind of get there. How do I like this table? Good question, James. How do you like this table? So I kind of think I just like xn and yn. So my x values, my y values, maybe we'll write the slope values too. I don't know. So yeah, sorry, I have to think here for always a little, this process to me always feels a little bit weird. So for n equals 0, that was our initial value. We were given that we had a starting place of x being 0 and y being 2. Let me go ahead and fix that over here. Also, if you have questions along the way, you should be asking them, right? You're welcome to ask questions, always, always, always. So now we're going to find the next y value. Well, let's find the next x value. So for n equal to 1, our x value is going to be 0.5. In fact, when I'm doing this, I kind of like to just fill in all the x values because they just increase by the same amount every time. So for n equals 2, our x value is going to be 1. For n equals 3, our x value is going to be 1.5. And for n equal to 4, our x value is going to be 2. Our y sub 1 is going to equal y sub 0 plus 0.5 times f of 0, comma 2. Let's plug in the values. We already know this answer, but I'm just doing it again to show how the work's repetitive. So y sub 0 was 2, and then we're adding on our rise. Our 0.5, which is our run, times our slope, which is 0 plus 2, which is 2. That gave us a value of 3. That's our y sub 1. Now to find y sub 2, which we also already did, we're just taking that new y value and plugging it in for y sub 1. So there's your y sub 1 plus, again, your 0.5 times f of your previous y value, previous x value, x sub 1, comma y sub 1, which in this case is going to be 3 plus 0.5 times 0.5 plus 3. I picked a very easy differential equation here, right? F of x plus y, f of x on y equal to x plus y, or dy dx equal to x plus y is pretty easy to evaluate each time. So then we're getting 3 plus half of 3.5, which is 3 plus 1.75, which is 4.75. Keep it going. Our third y value is going to equal y sub 2 plus our h times f of x sub 2, comma y sub 2, which is just going to be, there's your y sub 2 right there, 4.75 plus 0.5 times f of x sub 2, which is 1, and y sub 2, which is 4.75. So 1 plus 4.75. The numbers start getting a little bit gnarly when you do this enough steps. Like they just, you can kind of, unless someone's really thought out the problem very meticulously, the numbers are always going to get a little bit dicey. So here we're going to get, let's see, 4.75 plus half of 5.75 is 2.87. That's when you should use a calculator. Know what that is, but oh well. Let's see. So 0.5 times 5.75, 2.875. We add 4.75 to that, you get 7.625. Finally, one more step. So then to find y sub 4, we're going to get our previous y value, 7.625, plus half of our previous y value plus our previous x value. So it's going to be 1.5 plus 7.625. Every time, you just previous y value plus the run or the h value times whatever your slope is based on whatever your derivative would equal at the previous point. So we're going to get, let's see, that's going to be 7.625 plus, let me just do the math here, 1.5 plus 7.625 divided by 2 plus, so that's going to be 4.5625. If we add 7.625, we're going to get 12.1875. And what we're saying with this value is that this is approximately equal to y of 2. So y of 2 is approximately 12.1875. Is that a good estimate? Oh, sorry, you can say it. Is that a good estimate? Maybe. Let's find out. So, sometimes you could have actually solved the differential equation. This original differential equation, we could totally solve. Let's do that. And then we'll look at another example after that. So, let's solve dy dx equal to x plus 1. So question, is this differential equation separable? Definitely not. It's like kind of the most not separable, right? We're stuck. So it's not separable, but we know we can solve it, or at least we're told we can solve it. It's got to be first order linear. Those are our only choices. So it's going to be first order linear. So we're going to rewrite it as dy dx, or y prime if you prefer. We're going to bring the y over to the other side. So minus y equal to x. What's our p of x here? Right. So our mu of x, our integrating factor, is going to be e to the integral of -1, which is just going to be e to the negative x. As you're well aware, I'm a fan of doing the whole process of multiplying through by the integrating factor. So we multiply everything by e to the negative x. We're going to have e to the negative x times y prime plus negative e to the negative x times y equal to x times e to the negative x. Again, as we've said before, the whole reason for doing this is because every time you do this, the left-hand side of this differential equation becomes the derivative of a product. Specifically, the derivative of the product of your integrating factor times your function y. So then we're going to get that this is equal to x e to the negative x. And then we're going to integrate both sides and get that e to the negative x times y is equal to the integral of x times e to the negative x dx. And we probably could have skipped those steps and jumped straight to saying, okay, our function y is equal to 1 divided by your integrating factor multiplied by the integral of your q of x, or that's the thing on the right-hand side all by itself, times your integrating factor. I know I've said it many times, I'm going to say it again. Don't make the mistake I used to make and cancel those integrating factors. They don't cancel. We have to do the integration first. I would do two things here. Thing one, I would rewrite this as just e to the x, as opposed to 1 over e to the negative x, times the integral of x e to the negative x. It just feels like a nicer way to write it. And then to do this integral, we have to use integration by parts. So integration by parts, we're going to let u equal x, dv is going to be the rest, e to the negative x dx, du is dx, and v is negative e to the negative x. So this is going to become equal to e to the x hangs out, and then we multiply u times v, so we get x times negative e to the negative x, minus the integral of v times du, so minus the integral of negative e to the negative x dx. Finishing that off, we have e to the x times negative x e to the negative x, minus a minus is plus, but then we're integrating e to the negative x, which is again negative e to the negative x, plus c. I would choose to distribute the e to the x here and get that our solution is that y equals e to the x times e to the negative x is going to be e to the 0, which is 1. So we get a negative x, and then e to the x times negative e to the negative x is minus 1. And then we get c times e to the x. And then we can plug in our initial condition, which was y of 0 equals 2, to get that 2 equals 0 minus 1 plus c e to the 0, which is c times 1. So it looks like c is equal to 3. So our actual final solution here is y equals negative x minus 1 plus 3 e to the x. And now we can answer the question, is our estimate good? By plugging, and the answer is going to be, I don't really know, because like maybe it is, like how good is it? Let's find out. If we plug in 2 for x, we're going to get that y is equal to negative 2 minus 1, so negative 3 plus 3 times e squared. Where's my e button there? Where is the e button on this calculator? Good question. Where are you? Not that seems impossible. This calculator doesn't have an e to the something button. I'm mildly surprised here. Oh, there we go. Just hiding from me. Okay, so that is approximately not great. So here we're getting that y of 2 is approximately 19.16. So our estimate of 12 point something, not great, but it's what we got. Yeah, sure. So another way to look at this is if you actually look at the direction field for a second. Sorry, 1 second here. Take your time, yeah. Sorry, there we go. Which of these do I want? Good question. I just want that. Sorry, it's been a while since that is not the right one. You're fine, I guess. So if we look at dy dx equal to x plus y, there's our direction field. And then if we start, I would love to make this window a little bit bigger though. Sorry, 1 second. Not going to give me that. I picked one I don't really love here. Sorry about that. Sure, maybe you're better. Sorry, it's been a minute. Oh, wow. What are you? Okay, yeah, you're fine. Okay. So instead, if we pick this one here and move you over here. Oh, there we go. The one I wanted. Great. So if we graph this one instead, and then this is what happens when you don't plan ahead. I don't remember where the yeah, okay, there we go. So we want to make this, sorry, 1 minute. So there, if we look at that, and then if we started our initial condition of 0, 2, which is about right here. And if we, wow, we need to go out a little bit further here. So then you can see, oh yeah, if we look over here at 2, the value is about 19. And the idea of what we're doing here is the idea is that instead of actually finding that green solution, what we're doing with this estimation instead is we're saying, okay, at this point right here at 0, 2, we're going to take the path of that tangent line there and go over there. And then there, if you can follow my cursor, at that point, we're going to follow the path of that tangent line right there. And then here, we're going to follow the path of the tangent line right there. And then here, we're going to follow the path of the tangent line right there. So we end up with an estimate that's under because of the way those slopes happen to look. it's not a bad process for finding the estimate, it's just not going to produce a very accurate estimate. But that is kind of what the idea of Euler's method is that you're just using each point to kind of point you in the right direction to get to the next point, and then you just do it again. So let me show you. No, let's see. So should we do another example? Okay. The process is a bit tedious. I'm actually going to grab an example from Grant because I don't want to just make one up that's going to suck. Oh, except let me do that here. Sorry, 1 second. Let's see here. There's Grant. Good old Grant. Can I keep that on? Maybe. Let's look over here. Maybe someday, James. So scroll down here. Where are these Euler's methods ones? Where are the Euler's methods things? Let's see. Euler's method, graphically and numerically. So I'll point out, here's another example. So here's actually the direction field given, and the idea that if you're starting at y of 0 equal to 2, you're looking at the slope of the tangent line, you're following that for half of an x value, right, 0.5, and then at this next point, you're then doing the same sort of thing. You're saying, great, from there, we're going to follow that in that direction for x equal to half, and then from there, the slope of the tangent line is very flat, and then from there, so the tangent line is not so flat. So we're getting an approximate value of 1.5 after 4 steps here for this differential equation that we don't know what it is yet. Is it the same one I was doing? Where is the difference? Oh, there it is. There's the differential equation. So let's go ahead and work through that one because it's not a bad example. And then you can also, I can post this solution on Canvas as well so that you can take a look at it more closely if you want to. 1/2 x minus 1/2 y. I had these things printed out in my office too. And I didn't. I forgot. I kind of forgot about Euler's method. I was like, "Oh, we're done with chapter 7." So let's look at actually 2 versions of this example. So let's say our equation is dy dx equal to 1/2 x minus 1/2 y. I should actually say. You can use x or t typically, right? It's usually written as either x is your independent variable or t is your independent variable. It doesn't really matter what you're calling it as long as you're consistent or doing whatever is being done. Our initial condition is going to be, again, y of 0 equal to 2. And we're actually going to start off with a different situation. So the first version of this problem we're going to do is we're going to make our step size equal to 1. And we're again trying to estimate or approximate y of 2. So in this case, we're just going to have to do this twice because we know that for our initial value, for n equal to 0, our x sub 0 is just 0 and our y sub 0 is just 2. That's your beginning x value, that's your beginning y value. So we're going to do this once to approximate y sub 1, or y of 1, I should say, and then we're going to do it again to approximate y of 2. So challenge yourself for a moment here. See if you can write down the formula for y sub n plus 1. I'll remind you that it's equal to the previous value multiplied by the slope, which is your run times your, plus your rise, which is your slope times your run. All right. So I should move that picture of myself because it is definitely in the way. So the previous y value, well, we're talking about y sub n plus 1. The previous y value is y sub n. And trying to find the rise, which is the run times the slope. The run is always your h value, which in this case is always going to be 1. And your slope, you could write dy dx, but I might have done you a disservice here by not saying this. We typically call this f, capital F of either x comma y or p comma y, depending on what you're using. That's going to be your f of x sub n comma y sub n. Go away. There we go. All right, so our y sub 1 is going to equal our y sub 0, which is going to be 2, plus our h, which is 1, multiplied by f of 0 comma 2, which is going to equal 2 plus f of 0 comma 2 is going to be 0 minus 1/2 times 2, which is just going to be negative 1. Be 2 plus 1, which is 1. So our for n equals 1, our x sub 1 is 1, and our y sub 1 is also 1. Okay. To find our next y value, same deal. It's the previous y value plus our h times your derivative evaluated at your previous x value, comma, your previous y value. Which in this case is going to equal previous y value. Well, that's 1. That's what's going in right there. Our h value is always 1 so far in this problem. And then f of x1, y1 is just going to be f of 1 comma 1. Just plugging in previous x, previous y. Right. So yeah, it should be 2 minus 1. I certainly got the right answer, but I wrote the wrong thing here. That should be a 2 plus negative 1. Sorry about that. Right, that was definitely 2 plus negative 1. So then we're going to get 1 plus 1 times 1/2 minus 1/2, which is 1 plus 0, which is 1. So our y sub 2 is also 1. How exciting. So graphically, here's what we did. We started at 0 comma 2. And then the next y value we ended up at was 1. So we went over 1 and down 1 to get 1 comma 1. That was our first path. And then from there, we went over 1 and we didn't actually change our y value at all. So we went this way. So that's the path that our direction field pointed us in, even though we don't see the direction field here because I don't have it. Yeah.
Y sub 2.
Mhm. So each x value, and that's actually a great question. So all of these, the difference is always just h.
Oh, so it's the same as that.
In this case, yes. If h is 1, then your x sub whatever will be equal to n. But in the previous example, right, exactly. We're always just increasing the value of x by whatever h happens to be, whatever we are told that h is equal to. Because almost always in these problems, you are given the step size. All right, let's do it again, but let's make it so that h is now 1/2. The same problem, but now h is 1/2 instead of equal to 1. Do I have enough room? No, I do not. Let's do it down here. So now h is equal to 0.5. And just so we have it here, we still have the dy dx is equal to 1/2 x minus 1/2 y, which we are calling f of x. And I didn't do something in this previous one that I maybe should have when I was writing my table out, which is that I like to write all the x values right away. So I've got my n, my x sub n, my y sub n. We know that we're going to go, well, our x sub n is going to start at 0 because we know that f of 0 is equal to 2. Sorry, not f of 0, apologies. Y of 0 is equal to 2. So our x sub 0 is 0 and our y sub 0 is 2. And then our x value is just increased by whatever your step size is. So our next x value is going to be 0.5. After that is 1. After that is 1.5. After that is 2. So we're going to have to do this 1, 2, 3, 4 times to get to the place where we're going to get the right y value, or the estimate of the right y value. Right. So I would probably try to do as little writing as possible when you're doing this. I'm kind of writing everything I can, but you should, when you do this on your own, try to be, I don't know, streamlined. So y sub 1 is going to be y sub 0, which is 2, plus our h value, which is 0.5, times our slope, which is going to be f of 0, comma 2. And again, I'll point out, that's my y sub 0, that's my h, that is my x sub 0, y sub 0. So let's see what we get. That's going to equal 2 plus 0.5 times 1/2 times 0 plus negative 1/2 times 2. So it's going to be 0 minus 1/2 times 2. Make sure I get this right this time. So that's 0.5 times negative 1. So I have 2 minus 0.5, which is equal to 1.5. That's my y1. So graphically, we've started at the same place, but now we've gone over a half and down to a value of 1.5. So we're actually still, not surprisingly, followed the same direction for that first bit, right? Because we started at the same place, the direction arrow would still be pointing in the same way. So we're going to end up right there at 1, 1.5. Sorry, 1/2, 1.5. And then we'll do it again. So now to find y sub 2, it's going to be the previous y value, y sub 1, plus same value for h. And then we have f of previous x value, comma, previous y value. Again, just to make sure everyone's clear with what's happening here. That's my y sub 1. That's again h. That's again x sub 1, y sub 1. So the next thing you're finding, y sub 2 in this case, is always based on everything in the formula being from your previous point, right? They're all x sub 1 or y sub 1, whatever those happen to be. And then we're just going to throw it into the formula. So we're going to get 1.5 plus 0.5 times, let's see, f of 0.5, 1.5 is going to be 1/2 times 0.5 minus 1/2 times 1.5, which is going to equal negative 1/2. Yeah, 0.25 minus 0.75 is negative 0.5. So we're going to get 1.5 plus 0.5 times negative 0.5, which is going to be 1.5 minus 1/4, which is going to be 1.25. So from this point here, graphically, we're moving over to x equal to 1 and down to a y value of 1 1/4. Green pen there. So slightly different path now. We're going to be right there. Because from that point there, we had a slightly less negative slope. Whereas in the other example, the first example, we started here, we went all the way over there because we had a larger step size. All right, 2 more steps. So y sub 3 is going to equal our y sub 2 plus our step size, still 0.5. Let's some room here, so don't make it terrible, times f of, I think mostly for the, oh, sorry, thank you. I think mostly the reason I like this table is so that when I find f of the previous x, y value, I can look at this and be, okay, there's my previous x, there's my previous y. I think that's actually where I'm really using it the most. So f of 1 comma 1.25, which is going to end up being 1.25 plus 0.5. And then f of 1 comma 1.25 is going to be 1/2 times 1, 0.5, minus 1/2 times 1.25, which is 0.625. That's going to be 0.125, and then half of that is 0.0625. 1.25 minus, because this is going to be negative, 0.0625, which ends up being a thing you use your calculator for. You almost always need your calculator for these problems, like it's just unavoidable. So we get about we get exactly 1.1875. So sure, graphically, we've moved over to 1.5 there, and then our y value is going to be slightly smaller than it was before. There. Finally, the last step. Assuming I haven't made an error, let's double check Grant's work just so that we can be sure I didn't make a stupid mistake. No, he did it as fractions. Brave. Actually, it's not. It's not totally how I would have done it, really. Fractions is probably the better way to go here. So, last stop. I know it's the last stop. How do I know I've done it enough times? Well, good. Right. Yeah. And I think this is actually also a good reason why it's good to make the table. So you can just be like, well, I'm going to go down to x equal to whatever the input needs to be, and that's where I'm going to stop. You could also like take the difference between y of 2 and y of 0, or there would be 2 and 0 is 2, and then divide it by the step size, and 2 divided by 0.5 is going to be 4. So we don't need to do this 4 times, but I think making the table is an easier way to see that. So let's see. Y4 is going to be the previous y value plus your 0.5 times f of your previous x, comma your previous y, which is super gnarly. That's going to be 1.1875. That's pretty, James. Yeah. Plus 0.5 times half of a half is 0.5 times 1.5 minus 0.5 times 1.1875. Whatever that happens to be. We can calculate it, I suppose. So it's going to be, let's see, 1.5 minus 1.1875 times 0.5 times 0.5 again. So here's what we get. We get 1.1875 plus 0.078125. Which ends up being 1.26562, 1.26565. So we actually got a little bit bigger. So at this last step here, our direction arrow was pointing us in a slightly upward direction. So we're going to end up like right there. So depending on your step size, your estimates will be a little bit different from each other because they should be more accurate the smaller your step size is. I don't want us to solve this differential equation, but if we solved it and actually plugged into, we should see that this estimate here, this estimate down here is a better estimate of y of 2 than our previous estimate of it being equal to 1. I hope. So one of this method is a little bit tedious, but it is very manageable if you are good at it's really more of like a bookkeeping exercise than a calculus exercise. Like once you understand what you're doing, it's just making sure you're keeping track of things very well and being extra careful with that. One reason you might actually find it useful in this class is, so both of these examples we did are differential equations that one could actually solve. But there are plenty of differential equations that can't be solved, or at least can't be solved with the methods that we have. And for those differential equations, you could actually use this to estimate the value of your function at a particular x value, whereas you wouldn't really have any other means of doing that. So that's actually where it might be really useful in at least some abstract way. Again, the idea here is that these differential equations can represent some actual like physical model of something. And then if you're trying to find like how much stuff is there when 2 minutes have passed or 2 units of whatever have gone by, we can estimate that with this process. All right. I think that's all I should say about Euler's method. Usually I'll say one more thing. On an exam, if it shows up on an exam, it's typically going to be like 2 or 3 iterations. Like after that, it's usually going to devolve into grossness. So if you do see it in an exam, it's usually not too terrible. Usually. No guarantees. I'm not writing anything. All right. So now we can move on to chapter graphing in 3D. And then vectors shortly after that. So let's plot a point. Plot the point 2, 4, 6. And there's usually a couple different ways of setting up the 3D coordinate system. I prefer to do it this way, and I think most people prefer to do it this way, where you kind of draw your y and your z-axis, kind of like your old x and your y-axis, and then the x-axis is like shooting out towards you. So here comes the x-axis, like that. There's your 3-dimensional coordinate system. And then if we want to find the point or plot the point 2, 4, 6, we're going to move 2 in the x direction, 4 in the y direction, and 6 in the z direction. So we're going to go 1, 2 in the x direction, 1, 2, 3, 4 in the y direction, 1, 2, 3, 4, 5, 6 in the z direction. So you have to find the point that has all 3 of those things. So here's how I usually do this. We usually graph a point in 3 dimensions by graphing or drawing the box that kind of has those lengths as each of its side lengths. So I'm going to go 2 in this direction, and then I'm going to go parallel to the y direction. And then from here, I'm going to go parallel to the x direction. So I can find that point there, which is the point, well, x is 2, y is 4, and I still haven't moved in the z direction at all. In fact, it's probably not a bad idea to label all these points. So that point right there, where y is 4, is the point 0, 4, 0. You haven't moved in the x or the z direction. This point over here is the point 2, 0, 0. And this point up here on the z-axis is 0, 0, 6. Okay. To find the point where kind of z and y cross each other, I'm going to move parallel to the z-axis, and then from the z point, parallel to the y-axis. That point there is going to be 0, 4, 6. The axis that's hardest to move parallel to, if you're bad at drawing like me, is the x-axis, because it's not like a perpendicular deal, it's slanty. So from the point 2, 0, 0, I'm going to move up parallel to the z-axis, and then from the z point, I'm going to move towards you parallel to the x-axis. Like that. So there's the point 2, 0, 6, and then finally, to find the point I'm actually looking for, I'm going to either move from that point parallel to the y-axis, from this point parallel to the z-axis, or from this point parallel to the x-axis. And that point right there, that's the point I'm actually looking for. 2, 4, 6. Some people would describe it as the corner. So it's the corner opposite the origin of the box with x dimension 2, y dimension or length 4, and z dimension or length 6. 2 in the x direction, 4 in the y direction, 6 in the z direction. So you have a box that has side lengths 2, 4, and 6. Okay. A few other things here. A couple other things that are noteworthy. In 2 dimensions, we have 4 quadrants. Quadrant 1, where everything's positive. Quadrant 2, quadrant 3, quadrant 4. Which makes sense because each axis divides the 2-dimensional plane into 2 more things. So like if you have just the x-axis, it divides it into the top half and the bottom half. And if you cut that in half, you're dividing that into 2 more halves, so you get 4 quarters. And then if you divided that in half again, you'd have, instead of 4 things, you'd have 8 things. So in 3 dimensions, instead of having 4 quadrants, we have 8 octants. And we don't really care so much about labeling or naming them, except for the first one. So just like how in the 4 quadrants, the first quadrant is the one where all things are positive, the same is true for the octants. The first octant is the one where all things are positive. So the first octant is where X, Y, and Z are all positive. Just like the first quadrant, X and Y are both positive. So the first octant is the one that's like kind of the one we try to draw that's kind of facing you the most. So it's this one here where X, Y, and Z are all positive. So if you want to kind of block it off, it's this stuff out here in front. So typically, when I start talking about things and like trying to imagine things in the room, I usually like to think of the origin as that corner of the room over there, and then we're all sitting in the first octant of 3D space. And then if you went to like to the left outside the window, that would be where Y is negative. If you went behind the wall back here, that would be where X is negative. And if you went underneath the floor here, that would be where Z is negative. But we're living in the room where everything's positive. We're also happy. All right, so let's talk about planes. There's a few planes we want to be aware of. We typically call them the coordinate planes. So there's the XY plane. Try and draw things somewhat nicely here. We often, when we draw this, we just kind of draw the first octant, which is why I was talking about it. So we're talking about the XY plane. We're living down here on the floor. And on the XY plane, what's true? Well, if you're on the floor, you have no height, meaning that Z is equal to 0. That's the equation of the XY plane. Z equals 0. In a similar way, if we look over here at the YZ plane, YZ plane, well, in the YZ plane, if you're back against the board here, I haven't moved towards you or away from you, X is 0. Trying to use colors here. And thirdly, the one that's always a little bit sketchy to draw here, for the XZ plane, which is this one over here. Again, notice how I'm drawing the kind of boundaries of the plane using lines that are parallel to the axes I'm talking about. For the XZ plane, I'm going to draw a line parallel to the Z-axis and a line parallel to the X-axis. For the XZ plane, not surprisingly, Y is equal to 0. Now, there's lots of other planes, right? These are not the only planes, but these are the coordinate planes we talk about. And they're kind of important sometimes. We can also talk about other planes by kind of picking x, y, or z equal to a different value. For example, if I wanted to say graph the plane z equal to 3. So now I'm just shifting the entire xy plane up 3 units. So it's going to look like, instead of being the floor, I'm going up 1, 2, 3. And then, oh, I know what I was going to say. Another way to kind of think about this plane I'm drawing here is that if z is equal to 3, well, in fact, let me actually go over here for a second. If you were graphing the line in 2 dimensions, y equal to 5, you'd go up 5 units. And then what direction would you draw it in? Right, parallel to the x-axis, because this equation doesn't have any x's in it. You have freedom of movement in the x direction because there is no restriction on what x is. And it's not, right, you know what the line y equals 5 looks like. It's just this horizontal line where literally x can be anything. You get the point, 1, 5, 2, 5, 3, 5, negative 7, 5, any x value you want, 5. The same idea is true here. If we're going to graph z equal to 3, we're going to go up to a value of z equal to 3, and then you can move as much as you want in either the y direction or the x direction. So we get this plane that's been shifted up 3 units from the xy plane. It's kind of neat. Okay, I don't want to spend too much time talking about 3D graphing because at least I didn't on the from the lecture yesterday. It looks like he talked about it like not even this much, right? Like I feel like I'm doing more than he is doing. So I'll say one more thing about 3D graphing, and then we'll start talking about vectors. So the only other thing I want you to really be aware of, well, actually, there's 2 things. Sorry, 2 more things, and then we'll talk about vectors. So one is that the thing I've kind of just talked about, how if you're missing a variable or 2 variables, you have freedom of movement in that direction. So for example, for 2 examples, let's say I wanted to graph the equation x squared plus y squared equal to 9. If I was graphing this in 2 dimensions, what kind of shape would I have? Yeah, this is a circle. So in 2 dimensions, it's a circle, radius 3, it looks like that. But in 3 dimensions, well, I'm still going to get that circle of radius 3 in the xy plane. And then we have freedom of movement in the z direction. So we're going to say, okay. Thanks. So if I draw my circle of radius 3 in the xy plane, so on the floor, I always think of as the xy plane as the floor. I'm going 3 to the left, 3 to the right. I typically don't like to make the little marks on the x-axis because perspective, right? If something has a length of whatever in the one that like is perpendicular parallel to you, and you tilt it, it doesn't look as long anymore. And I find it hard to kind of make the units look the right length. So I'm just going to try and mark those off at 3 and then try to draw the circle that would be lying flat. There you go. That's a circle lying on the ground. And then we get to move that circle in the z direction as much as we want. So we can either move up or down. Oh, what shape do I have? Cylinder. So this is a cylinder in 3 dimensions. Okay, we're going to do one more shape like this, then we'll talk about one more thing because I just want to point out a naming thing that's kind of weird. So what if I wanted to graph? Yeah, sure, that one's fine. Z equal to x squared plus 1. Well, if this was a 2-dimensional graph, thinking about what's happening just in the xz plane, What kind of shape would that be? Like if it was y equals x squared 1, that's x squared plus 1, that's going to be a parabola. So in 2 dimensions, parabola. In 3 dimensions, I'm going to take that parabola and I'm going to extend it in the y direction. Which always feels challenging to me. So the hard part about this one, I think, is also you're drawing this in the xz plane, meaning, again, it's kind of tilted. So here's my parabola in the xz plane. Yeah, I can do an all right job of drawing this. Oh, I didn't shift, darn it, I forgot to shift it up by 1. Sorry, I didn't shift it up 1. Fine, we'll grab z equal to x squared here. Apologies, sorry, I meant to shift it up by 1. And then we're going to extend it in the y direction. So we're just going to say, great. It's kind of like, I kind of like to imagine it like drawing a curtain. Like if you took that little thing down there, if that was your curve and you just pulled it down, that would be like extending it in the direction you're extending it. So we're kind of like taking this curve, just like imagining like there's like a curtain attached to it and like pulling it out this way to make it one surface, which still looks parabolic. So if we draw this curtain out this way, and then make sure it still looks the same, do our best here. That's pretty good. What we have here is a surface that kind of looks like you've just taken it. In fact, it kind of looks exactly like this. Right, there's your surface. And what do we call that? We call that a parabolic cylinder. So it's kind of a weird naming convention, but when you have a curve in 2 dimensions and you extend it in the 3rd dimension, we usually call it the name of that curve cylinder, which is kind of weird, but it is weird. So if like it was an ellipse and you pulled it out, it would be an elliptical cylinder. Or if it was a hyperbola and you pulled it out, it would be a hyperbolic cylinder. Or if it was a other 2-dimensional shape that's curvy, like I'm trying to think of other ones I don't know. Like there's not a lot of other 2-dimensional shapes we really talk about, so that's what you get. All right. The last thing I want to talk about 3D graphing wise is just spheres. And really, I don't so much care about graphing them because I think all of us can draw a circle somewhat decently, but the equation of a sphere. So the equation of a sphere. So here's an equation of a sphere. X minus 3 squared plus y plus 2 squared plus z squared equal to 25. And in a very, very, very similar way to the equation of a circle, we can easily identify the center and the radius. The center of this sphere, just like with a circle, is the coordinate that makes the left-hand side of this equation equal to 0. So x needs to be 3, y needs to be -2, and z needs to be 0. The radius, just like with a circle, is the square root of the number that's on the other side. Which in this case is 5. It would not surprise me at all if you were given something like this on an exam, like the following question on an exam. So I would say something like find the center and radius of the sphere x squared plus 8x plus y squared plus z squared minus 6z equal to 24. So I'll point out, unlike the previous sphere equation, this sphere equation is not written in the standard way. It's not x minus something squared plus y minus something squared plus z minus something squared equal to some nice number, or even some not nice number. So to finish this off, to make it look like the standard way of writing, we have to complete the square for x, y, and z. Well, specifically here for x and for z, because y squared, there isn't a plus y term. That y squared is already completed. So for x squared plus 8x, we're going to rewrite this as x squared plus 8x plus we're going to leave ourselves some space. y squared is on its own, and then we have z squared minus 6z. We're also going to leave ourselves some space. And on the other side, we're also, whatever we add to the left, we're also going to add to the right. What do we add? Well, we add the thing that completes the square. So for 8x here, we take the 8, we divide it by 2, we square it, that's 4 squared, that's 16. We're going to add 16 on both sides. So you all should then be able to tell me for the z squared minus 6z, what are we going to add to both sides for that? We're going to add 9. Negative 6 divided by 2 is negative 3. Negative 3 squared is 9. Better question. Why are we adding these things to both sides? Well, they allow us to rewrite x squared plus 8x plus 16 as something squared, right? This is going to turn into x plus what squared? I know you know. What numbers multiply to 16 and add up to 8? 4 and 4. Oh, it's x plus 4 times x plus 4, which is x plus 4 squared. And then we've got y squared on its own, doing its own thing. And then same deal here. For z squared minus 6z plus 9, what numbers multiply to positive 9 and add up to negative 6? Negative 3 and negative 3. So you're going to get z minus 3 times z minus 3 or z minus 3 squared. That's why it's called completing the square, because you're literally adding the number that helps you write it as something squared. On the right hand side, you may or may not get a nice square number. We happen to get one here. We get 49. But if that number was like 33, then you would say your radius was the square root of 33. Here, our center is negative 4, 0, 3. Our radius is the square root of 49, which is 7. Sure, so that's the typical process for completing the square, because what we're really doing here is we're saying, if I want to write, let's see, yeah. So if I want to write, like, say, x squared plus any number you want, I'm going to make it general. It's going to be kind of funky, but we'll do it. X squared plus b times x. If I want to write that as something squared, what I would do is I would write it, and let's say it's equal to, that's kind of silly, James. Sure, we're just going to complete the square. So we're going to add on half of b squared. And the reason we're doing that is because this fact, so the reason we're doing the thing we're doing is to get the result we want. Because when you add this number on, whatever it happens to be, this is always going to factor as x plus b over 2 times x plus b over 2. Because when you multiply it out, you get x times x, you get x times b over 2, plus another x times b over 2. And then you get b over 2 times b over 2, which is b over 2 squared. And then this middle term here is just b times x. So that's the process for completing the square. Just taking that middle term, dividing by 2, squaring it, adding it, and that allows you to rewrite things. The other thing I wanted to mention here is that this equation of the sphere also kind of informs us about the distance equation, distance formula. So I will point out that for this sphere here, for the sphere x plus 4 squared plus y squared plus z minus 3 squared equal to 49, which I'll draw kind of haphazardly here. There's my sphere. The center was 4, 0, 3. Sorry, negative 4, 0, 3. And any point on the sphere is a distance of 7 away. I'm going to call that point x, y, z. So the distance between x, y, z and negative 4, 0, 3 is 7. And I'll point out that if you square root both sides of this equation, we get that the square root of x plus 4 squared plus y squared plus z minus 3 squared is equal to the square root of 49, which is 7. And this left-hand side really just represents the distance between the point x comma y comma z and the center -4 comma 0 comma 3. If you want to find the distance between 2 points, the distance formula in 3 dimensions is essentially the same as it is in 2 dimensions. You're just adding on a third piece. So more generally, the distance between 2 points, x1, y1, z1, and x2, y2, z2 is exactly the square root of the difference between the x's squared plus the difference between the y's squared plus the difference between the z's squared. All right. Well, we'll start talking about vectors and we'll continue talking about vectors on Thursday. So vectors. How to draw them? Well, let's draw some vectors. So actually how to write them, first of all. So let's plot or draw the vector v equal to, I would say there's probably like 3 typical notations. My favorite's probably this notation, like that. Other equally good notations are to write it as a matrix like this. Some people do like to write it as brackets with a comma. Did he use any of these in class? This one here? Oh, but I mean, like, as far as like this one here? Okay. Parentheses, that's like the worst choice. And the reason I say it's the worst choice is because we already used normal parentheses to indicate what a point looks like. So that's why I typically don't like to use normal parentheses for my vectors, because I feel like it's easy to confuse with the point. So if I was going to draw this, typically, if we're not given any other indication, we draw a vector by thinking about it emanating from the origin and terminating at the point that you would get if you plotted the point 3, 4 in this case. So we're going to go over 3, up 4. There's my vector v. Which you might right here, you might write there. A vector has both direction and magnitude. Magnitude, just a fancy word for length. The way you write the magnitude of the vector is with what you would imagine is an absolute value symbol. Although when you see the absolute value of a vector, you shouldn't say it's an absolute value. You should say it's the magnitude of the vector. So this symbol around the vector means the length of the vector. So the magnitude of the vector is going to be, well, if I want to find the length of this segment, I'm just going to think about the distance formula, right? I'm going from 0, 0 to 3, 4. So you could do it the hard way and think about it being the distance formula. Or you could just say it's going to be the square root of the components of your vector squared and added together. I don't really need to do 3 minus 0 squared plus 4 minus 0 squared. That's going to be the square root of 9 plus 16, which is the square root of 25, which is 5. So this vector has a magnitude or length of 5. And the direction is something we don't often really actually talk a whole lot about. Or if we do, we kind of say, well, the direction is the vector 3, 4. Like you're going over 3 and up 4. That is the nicest way of describing the direction, really. Question there?
Yeah, I thought the distance formula was from the Pythagorean theorem.
It is. You're exactly right. So it's coming from the fact that this base is 3, this height is 4, and the magnitude of this length here is exactly what we're saying. The magnitude of the vector squared is equal to the sum of the squares of the bases.
And so is that the same for, is that any different for like three-dimensional?
No, in that it's still going to be exactly so it's no different in that the way the three-dimensional distance formula is no different. We're just adding on an extra piece.
Okay.
So for example, just as a quick aside here, if your vector in 3 dimensions was say the vector 2, 1, -2, then the way you'd find the magnitude of that vector would be the square root of 2 squared plus 1 squared plus -2 squared.
Okay.
It's just always so, and in fact, even though we don't really talk about vectors in higher dimensions in this class, it's still a thing that exists. And the way you find the magnitude or length of a vector in dimension 4 or 5 or 6 is you take all the components, all 4 or 5 or 6 of them, square each of them, add it all together, and take the square root. So the distance formula is always the same. We can always extend it to higher and higher dimensions.
Okay, and then for the sphere,
Mm-hmm.
why did you subtract the 2 points earlier? So it was like x1 minus x2.
So I was kind of trying to talk about how the sphere leads to the distance formula. Because we know that every point on the sphere, whether it's there or there or there, all these points are the same distance away from the center. And that's kind of what makes a sphere, is that every point on the sphere is what the radius is away from the center. But then I was saying, well, look, we've got this formula here, and actually I'm going to rewrite it. Sorry, you can't quite see that. I'm going to rewrite this so it looks a little more like the distance formula. This is really x minus -4 squared plus y minus 0 squared plus z minus 3 squared. So the way we're finding, well, and that's equal to 49, and if you square root both sides, you're exactly getting the square root of x minus the other x coordinate squared plus y minus the other y coordinate squared plus z minus the other z coordinate squared equal to the distance between those 2 points. So I wasn't really trying to like say anything super unique about this other than just like it naturally kind of arises from the equations here. But you totally could have done it with a Pythagorean theorem kind of thing as well, where you can say, I got it in there. So another way to have done this, right, instead of just kind of using this and getting the square root of 4 plus 1 plus 1 plus 4, sorry, which is going to be the square root of 9, which is 3. Here's another way to approach this. I'm going to need more paper though. We got this. So let's say I wanted to find the actual length of this, thinking about it in the Pythagorean theorem sort of way. And yeah, I can probably draw this. Okay. So we're going to go over 2, down 1, right 1, and then down 2. Kind of funky. It might not be. I think I'm going to try and make. Let me give you an example. It's a little easier. Let's say we want to find the length of the vector, the new vector. Let's call it u equal to. Let's make things nice and positive. Let's say it's 2, 1, 3. I'm just going to deal with the 2, 1 part first. So we'll draw this in a second, but let's actually look in 2 dimensions for a minute here. So we look in 2 dimensions just for a moment. You give an x coordinate of 2, a y coordinate of 1. We go over 2, up 1. Then the length of this part here, which we'll draw in our 3-dimensional setup in just a second, I promise. I'm going to call this vector v. The length of v, well, Pythagorean theorem, it's going to be 2 squared plus 1 squared equals the length of v squared. So 2 squared is 4 plus 1 is 5. So the magnitude of v is going to be the square root of 5. Okay, so now let's draw this vector in 3 dimensions. So we're gonna go in the x direction 2, in the y direction 1, and then up 3. So what I want to point out though is that going 2 in the x direction and 1 in the y direction gives me this length here, and that length there is a length of the square root of 5. Right? That's that part right there. That part right there, that's your length of v, which is the square root of 5. And then to find, again, I unfortunately I should have picked something that had a longer y part, sorry. So then to find the length of this vector here, which is, oh, geez, the drawings are terrible, sorry. So to find this vector here, which terminates at the point 2, 1, 3, well, I have a right triangle there. So actually I'm going to take this triangle and draw it so it looks nicer. So here's my right triangle drawn in a better way so that the base is my root 5 and the height here is my 3. Can you see what I'm doing there? So then I'm going to try and find that length there, the magnitude of my vector u. That's going to be the hypotenuse of this triangle here. Okay, we can find this. So the magnitude of u squared is the square root of 5 squared plus 3 squared, which is 5 plus 9, which is 14. So the magnitude of the vector u is the square root of 14, which I want you all to recognize is equal to the square root of 2 squared plus 1 squared plus 3 squared. Because what you're really doing is you're saying, oh yeah, this v part here, right? When I do the magnitude of u squared equal to the magnitude of v squared plus the 3 squared part, well, the magnitude of v squared is just the other two components squared and add together already. So you're really just getting, oh yeah, that's your 2 squared plus 1 squared plus 3 squared. So that's why you can use this idea for finding the length of any vector in any dimension by just taking all the components and squaring them, adding together, and taking the square. And I guess I should stop there. We'll talk more about vectors on Thursday. I should say one more thing though. We typically draw a vector emanating from the origin. It does not have to emanate from the origin. So if you drew this vector that I started with here, 3, 4, if you drew it like from here instead, that vector there that starts at the point 3, 0 and ends at the point 6, 4, that would also be the vector phi. It's not any different. It's got the same direction and the same length. So for all intents and purposes, it's the same vector. We've just drawn it in a different location. All right, now I'll stop talking. You're welcome. Restroom is weird. It's at the end of the hall, and like go down some stairs, and yeah, there's a shower in there. If you had to pick a restroom that someone was going to kill someone on campus, it's the one that would feel the most likely.
Yeah. Thank you.
You're welcome.